All right, you'll notice something up here. Basically what you see up here is our standard equation sheet, right? So it kind of goes over all the various equations that we actually have. Used it on multiple tests. One thing to point out, it just changed it. They came up with the newest, updated equation sheet that you're gonna have on your AP exam. Now, this new equation sheet, I actually like it a little bit better. One of the reasons why I like it is look what they're giving you right here. They're giving you the prefixes. I think that is, I don't know. I think that once again, you should have probably learned the majority of these prefixes back in like middle school, elementary, conceptual physics, honors chemistry, but they're giving them to you. So they're trying to make it a little bit easier for you to kind of see things like hertz and you got volts. We're going to talk about today as well, kind of talk exactly what that's going to be. But it has all the equations on it. Also, one of the things that they added to the equation sheet, which I'm shocked they put it on there, but I think it's pretty cool, is they put that Coulomb there, Coulomb's law. So it's sitting right there and it shows you once again what the relationships are going to be. So when you start to talk about, hey, intermolecular attraction, okay, well I can talk about different things based upon the attraction force that might exist between these actual elements. So continuing on, so we've got this. Where we're at today, once again, it's got the acid base. They kind of threw everything up in there. They threw actually a few more equations on there as well pertaining to the acid base. And once again, Gibbs free energy. You saw that as part of your homework assignment. You should have saw this one in the video yesterday. Delta G is equal to negative NF of E, which is Faraday's constant. We'll talk all about this, which really means in the scheme of things, we only have 2 more equations to go over, and then we're finished. So it's my hopes that we're gonna be finishing this up tomorrow, which means if we can, that's gonna be perfect, because that aligns means on Thursday, if you remember, Thursday we have what? A double period. So we're talking all about the AP exam. You have an opportunity to study. You'll have, in a sense, those 2 periods. You'll have Friday, you'll have Saturday, you'll have Sunday, you'll have Monday, and then Tuesday you'll take the exam. Now, one of the things I'm going to tell you is I'll probably send out an email and let you know that, hey, over the weekend, and I do this every single year, I'm going to host office hours, meaning that you can come in and ask any questions you want. So as you're reviewing, you're going over something, or maybe there's something that you're having a little bit of difficulties with, like I need just a little bit more help with this particular topic. Can you go back and kind of just explain it? I will be there to try to help you in every way I possibly can over the weekend. And of course, Monday we'll show up, and then Tuesday you go down there, and then on Tuesday we are going to meet here, and I'll send the email, give you specific details. You'll come in here first, and then we're going to walk as a class and take our procession that we take every single year down to the gym, and then you'll take your actual exam, go in there, and hopefully end up getting really high scores in this case. All right, so what I want to do is I want to do the following. Oh, matter of fact, I'm going to pass this out. This is the new equation sheet, so you can have a copy of it. In a few minutes, probably right after this class, I'm going to be updating our equation sheet on Veracross as well. So if you need an extra copy and you misplace this copy, you have the newest and latest equation sheet. There we go. But for the most part, it's still the same. It just gave you a little bit more information, which I think is fantastic, actually. I like the new equation sheet. All right, continuing on. All right, so what I'm going to take a look at right now is we're going to take a look at a Voltaic cell. Now, Voltaic / carbonic cell, same thing. In the video yesterday, I think he mentioned this being a carbonic cell, didn't he? Okay. Also, I was watching the AP video today, so I was thinking about maybe giving this one as a video that you might watch tonight. And all she was talking about was the same way I talk about it. It's a Voltaic cell, Voltaic cell, Voltaic cell. Once again, used interchangeably in this case. So what we're going to do is we're going to take a look at this problem right here. So let me open it up really quickly. Go here, out here, go back here, and here we go. So it's going to be that worksheet that I just gave you, which is going to be this one right here. So basically what we've got here is we've got this Voltaic cell. And what you'll notice in the Voltaic cell is that basically what they did is they took a piece of copper metal. So here we go, piece of copper metal. In that actual solution, you'll see they went with some copper to aqueous solution. And once again, when it comes to this copper to aqueous solution, I just went over to my lab and I got copper, in this case, 2 sulfate. I can do copper 2 chloride, I don't care. Just so long as it's aqueous and I'm getting those copper ions in there, then I should, in theory, be able to produce this battery. So I'm gonna pour some of the solution on the side that has the copper. You know what? I'm gonna make sure that it kind of looks just like the diagram I have here. Here we go. The next thing I need to do is I got my zinc, in this case electrode. I've got some zinc chloride. I also have some zinc nitrate. Doesn't make a difference which one I choose. I can go zinc nitrate, put it in here, pour some water, get it dissolved. I just need those zinc ions to be present. So I'm gonna go with the zinc chloride since it's already dissolved in here. All right. Right now, once again, I can clearly see that this is gonna be the reaction that's gonna take place. And basically what's gonna end up happening is I can see, based upon, once again, this reaction, that I can go in here and write my half reactions based upon the reaction taking place. So what I want you to do is I want you to write the 2 half reactions that are gonna exist right here. So what are the 2 half reactions? And that's kind of what you had to do on that sheet that I handed you. I asked you, hey, write the 2 half reactions. Is it okay? And then once again, when I balance it, I'm gonna notice that in this case that, hey, you've got 2 electrons, you got 2 electrons as well. It's balanced in this case. I just need to bring the 2 together. And in theory, it was already presented to me as being a balance. In this case, redox reaction. So I'm just gonna go down here and say Zn plus Cu, 2 plus. And if you didn't put the states here, because I didn't give you the states here, it would be okay. Going to produce, in this case, where we say Zn 2 plus aqueous plus Cu as a solid. All right, with this said, let's see what's going on here. Is this oxidation or reduction?
Reduction.
It's reduction, right?
Yeah.
Reduction means, once again, the gain of electrons in this case. So I know that this is my reduction. Therefore, this by default, once again, the removal of electrons, oil rig, means that this part has to represent my oxidation. With that said, what AP is going to ask you to do is they're going to say, hey, you know what? On the metals up there, indicate which one's going to be a cathode and which one's going to be the anode. And if you remember, okay, your reduction over here, is this going to be my cathode or anode? Cathode. And once again, once I use the fact that, hey, you're a consonant, cathode's a consonant, hey, they go together, that's positive. Over here, once again, I know this is going to be my anode in this case. Also, one of the things that AP is going to ask you to do is it's going to ask you, hey, which direction is the electron flowing? Normally what they love to do for these problems, they love for you to just say, hey, put an arrow on there, indicating the flow of the electrons. Well, if you look at it, I can clearly see that the one that is going to end up losing the electron means that it's going from here, it's losing, and this one's going to take the electron on. So it always goes, in this case, from the anode over here to the cathode. So that's kind of like the flow of my electrons in this case. Now, of course, with this setup that I have sitting right here, if I take my voltmeter and I hook my voltmeter up to, you know what, I don't need these alligator clips. I'll just hook my voltmeter directly on to the alligator clip. Oh, here we go. We'll put this one here and this one right here. And when I turn the voltmeter on, let's turn this thing on. You're gonna notice that right now, it says, what does that say, Taffy?
0.
It says 0 volts. So right now, I do not have, once again, any sort of current or voltage going on with this thing. Now, of course, one of the things that we said that we need in this case is we need to add the salt bridge here. And we said the purpose of the salt bridge is to, once again, make sure there's a balance of charge in both of the containers. Because once again, as soon as this reaction takes place, the charge is going to be, once again, not in alignment. You're not going to have an equal number of charges, because what's going to happen here is this copper that's in the aqueous solution is going to say, hey, I'm going to deposit myself right onto this piece of metal, and I will be solid copper. I'm removing positive charge over here. Over here, you're going to have the zinc that's sitting here as an atom, a solid zinc. It's going to simply go in this direction, which means that the concentration of the positive charge is going to build up over here. Now, when it comes to a salt bridge, all I need is an aqueous salt. Hence the term salt bridge, an ionic compound. My go-to is just, hey, sodium chloride in this case. So in a second, I'm going to add a salt bridge here. In this case, I'm going to say, hey, my salt bridge happens to be NaCl aqueous. Now, what the AP loves to do is they love to say, okay, well, which direction are the ions going to migrate in? Because one ion is going to go this way, and the other ion is going to go that way. So cation is going to go one way, and the anion is going to go another way. Now, I didn't watch the video, but did they make a little hint? Because there's one easy way to figure this thing out. Like, I just know it like that. I don't even look at it. And I don't think they did. All right, look at it this way. If this one's removing positive charge, guess what I got to add to the side?
Or positive.
Positive. I'm going to make up for the positive charge that's being removed, right? All right, so over here, I'm going to end up having my Na plus, or we can say our cation kind of flowing over to this side over here. Which means that over here, where I'm adding, in this case, positive charge, I need some negative charge to kind of cancel out the buildup of the positive. So I'm going to have my Cl minus here, or my anion, flowing this way. Can anybody see a really quick, easy trick that you can use on the AP exam where I don't have to think my way through this?
Oh, wait, is this where it said like the red cat or something?
It's what?
Is this where like they like said like the red cat or something?
Oh, I don't even know. 'Cause I can't remember. I don't watch that video. But just look at it. What?
Your keton goes to your cathode and the anion goes to your anode.
Exactly. Hey, that's called a cathode. Positive charge, right? That's where my cation is going. That's my anode. Hey, negative charge, that's where it's going over here as well. So I kind of just use the charges here and I say, okay, well, clearly anion goes there, cation goes here. I've got it in this case. So, salt bridge. What am I going to do? I'm going to take a paper towel here. Another paper towel. And I need a beaker here. I need some salt. And unfortunate, I don't have any sodium chloride in there. But what I do have, and once again, it makes absolutely no difference. I got another salt. I got potassium chloride here. So all I'm going to do is I'm going to take this beaker. I'm going to add some potassium chloride. And I know that this salt is definitely going to be soluble. And the reason why I know it's soluble is, hey, it's got an alkali metal in there, right? Alkali-containing compounds are always going to be soluble. So I'm just going to take this thing, add a little bit of water right here, and get it dissolved. And I put there's some really big chunks that kind of got in there. I'm not going to sit here and try to get it on. There's enough in there. I've got, once again, aqueous potassium chloride sitting right here. So next thing I'm going to do, I'm going to take this paper. I got some scissors here. It's going to be my bridge, absolutely. Got to twirl this around just a little bit. You'll see why in a second. Just gonna put it in here, let it get some of that aqueous solution there. All right, now quick question. Anybody have a straw in them? Just a straw? Somebody
I might actually.
Do you really?
Yes.
Get out of here. Do you really?
Yeah, but I steal the straws.
Whoa, you borrowed.
Yes.
You borrowed a straw.
Follow up.
Man, and you know what? I was actually joking in this case. Cause I grabbed a couple of straws this morning, but hey, I might as well keep my straw in this case, especially since you're getting them for free. Here we go. So, what do we do here?
I knew I was gonna do that.
Is that gonna fit? That will fit. Take this paper out. Twirl it once again, get a little bit tighter here. And all I do is we kind of feed it through the straw. And actually, I like your straw better. The straw I have is actually a straw that you can't see through. This one I can see through it, so it makes it a little bit easier for me when I actually add it to see when it's starting to come out the other side. Come on, get in there. What's your straw? And I might do it a slightly different way if it doesn't go. There it goes. It's starting to feed through. And I'm going a different way. Give me 1 second. What I'm going to do is I'm going to actually add the dry paper to the straw first and then put the straw in the aqueous solution. Because as wet, it's just a little tricky to get it through there. I think as a dry, it's going to go a little bit easier through. Come on, come on. There you go. Got my salt bridge. Faster, faster, faster. Perfect. All right, let's try this again. There we go. A little bit easier for it to thread its way through. So that piece is going to get caught. I'm going to go all the way. I'm not going to have to cut the straw. Cut it. All right, perfect. Got our soft bridge. All right, and here we go. So I got my salt bridge. Make sure it's got on the inside of that straw. It's got to connect all the way through. There it goes, paper towels wet. All right, so if you look at the voltmeter, watch what's going to happen here. So here we go. Right now, once again, no voltage. Come on, chemistry, work for me. And you got voltage?
Yeah.
Okay. So once I add the salt bridge, then it allows for, once again, there to be that balance of charge to allow for this thing to proceed. Now, if we look at it, we've already identified in this case the flow of the electron. We said in this case it's going from the anode to the cathode. And then it says, hey, what does it say? Identify the direction the positive ion will move. We already said the positive ion from, and I needed to change that. That's from the salt bridge. Of course, it's going to move towards, in this case, the actual cation side, or the cathode side. Circle on the diagram the actual anode. Well, we already kind of labeled it, so it's okay for this one. The next one that we got here is it says put a box around the cathode. Okay, we already taken care of that as well. Put a plus or minus. Place a salt bridge. Show the direction of the ions in the salt bridge we showed. Now this is a good one. Which electrode is going to increase in mass? And then it says which ion concentration is going to increase. So if I look at it, look closely. Which electrode is going to increase in mass? The cathode or the anode?
Is it going to be the anode?
So the anode is going to increase in mass. Exactly, because you're depositing, in this case, solid copper onto the actual cathode. So its mass is going to actually increase in this case. How do I know this one as well? You're positive. This one's going to always increase in mass, and guess what's going to always happen to this one over here? It's going to decrease in mass because the solid zinc is just going into the actual solution in this case. So I can see that the mass is going to increase for the cathode, and it's going to decrease in this case for the anode. The next one I believe I was asking is, hey, which of the two containers is going to have an increase in its actual concentration in this case? In this case, I can clearly see it's going to be the container on the right or the container on the left that's going to have an increase in the concentration of the ions in the solution right here. The zinc, right? Because it's going from solid zinc into more aqueous zinc being produced. This one's saying, hey, I'm actually going to decrease my concentration because I'm taking this C2 plus and I'm depositing it back on, in this case, to the actual cathode. Anything else we got here? Oh, calculate the Ecell for this one. Now, for the Ecell, we're going to notice on the first page, right here, I give you this list of standard reduction potentials. Your predecessors, this is what they gave them. They gave them an equation sheet. They also gave them this sheet right here. They don't do this anymore in the AP. They actually give you the actual reduction potentials in the actual problem. But at the same time, all you're going to do is you're going to go in there and you're going to find the half-lives. I said the half-life. The half reactions that match up with the half reactions that you have. And keep in mind, this is a reduction potential table, so it's showing the reduction. It showed you in the video yesterday, if you want oxidation, all we do is flip it, right? And whatever charge that is, you treat it like a Hess's law. Hit it with a negative in this case. So go through and figure out what that Ecell is going to be. I need to go here. What else we had? Which one do I need? This one here. But luckily for me, oh man. Oh, thank you, because that's a 2 plus. See, like that. Thank you. All right, and if I look at the one I have up there, perfect. So I can go in here and say, hey, E, in this case, reduction, is equal to 0.34 volts in this case. Then I gotta find my zinc. Oh, where's zinc? Where are you? Zinc, zinc, zinc. There we go. And when I find my zinc in this case, I'm going to say, hey, you know what? This is actually shown as being reduction. I need it as being oxidation. I got to flip this thing around. And therefore, the Ecell, or the E of oxidation, is going to be equal to 0.76 volts, which means that my Ecell is just the combination of these two right here. And when I add them together, volts, 0, carry the 1, carry the 1, and it looks like you get 1.10 volts, right? Perfect. That's as simple as it is. It's that simple. If you think about it, if I want the cell to be spontaneous, I want it to produce voltage, I don't go to the grocery store and say, hey, let me go find a battery that says -2 volts. What? We always want volts to be positive, right? And that's what it told you in the video as well, that you're always going to make sure that it's positive. For a problem such as this one, I've seen it sometimes where they'll give you the actual 2-half reactions. And they'll give it to you, hey, this way here, and they'll also give you right here. So they'll give you this, and they'll say, hey, 2 electrons plus the copper 2 plus aqueous going to produce the copper solid. Hey, the E of reduction happens to be 0.34 volts. And they'll go in and they'll say, okay, you know what? I want a spontaneous galvanic cell. You tell me which one should be oxidized and which one should be reduced. If they say they want it to be spontaneous, then I know for a fact I can't just simply flip this one right here, because if I do flip it, I'm going to be taking something. I will change to be oxidized. But that's going to be a negative with a negative. That's not spontaneous. I need to just make sure that the two come together in a way in which it produces a positive E cell in this case. Positive E cell implies, once again, that it happens to be a spontaneous cell. Now, if you look at the next part, they ask you to go in and they want you to simply calculate what delta G is going to be. Delta G, once again, the nice thing about it, if you forget it, it's right there. Where's our new equation sheet? Right there. It says, hey, delta G is equal to negative N, Faraday's constant, and E. And remember, N is just the number of electrons that are being transferred between the two. So in this case, hey, the N will be 2. Faraday's constant, don't memorize Faraday's constant. Go to the equation sheet. They're going to give you, look at that right there. It's posted right there. And then all you're going to do is just add your E cell to it as well, which we already calculated. Here. So I guess something that should look like this. Negative 83 sig figs. We get negative 2, 1, 2, 0, 0, 0. 1, 2, 3, 2. All right, did you ever get this here? Now, the question is, oh no, what is the units? Well, we got to look at it. That's coulombs. Coulombs, of course, is, we just use a capital C for coulombs. Moles cancel out. So moles of electrons cancel out right here. The problem we run into is right here. I got volts and I got coulombs sitting right here. But that's okay, because if you look at it, all you have to do is just go right up here, and they tell you right here, go up, 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 that a volt is coulombs per second, right? Oh, I'm sorry, joules per coulombs, thank you. So if I go in here and I substitute this as the real unit, joules per coulombs, coulombs cancel out, coulombs cancel, it just gives you joules in this case. That's really what's gonna come out. Do you have to do all the conversion? If you can remember, hey, it's gonna be joules, put the joules, but put the units there. Do not just simply put the answer there and be like, I don't see any units, don't give that person any points in this case. The next question is asking, hey, is this actual cell spontaneous or non-spontaneous? Well, guess what? My delta G happens to be a negative value. So therefore, I know that once again, this is a spontaneous. Those, one sample takes a galvanic cell. All right. Everybody okay? All right, so what you are going to do is you are now going to try the next problem. And you got 5 minutes in which to solve this problem. Can't do that. That's contagious.
If they provided the state like aqueous solid, we have to include that in our.
I would if they asked me to write it. I just didn't want to take the risk of like, hey, in the rubric they want the aqueous. And I've seen sometimes where they leave aqueous off, sometimes in the rubric they put it there. If I know the state, I might as well just go ahead and give it to them. All right, let me just explain one thing here. What I'm going to do is I am going to release the answers to problem 1 and 2. So the answer is going to be right there on Veracross. I'm also going to give you the answers to 3 and also 4. It's just going to become repetitive for 3 and 4. If you're okay with 1 and 2, 3 and 4, the exact same thing. Just once again, I'm just giving you more and more practice problems. I'm going to give you the answers through 1 through 4. Your homework is going to say this on Veracross. Is you're going to pick up right here where it says actual AP chemistry problems. There are going to be 1 free response, and then you got like maybe 3 multiple choice questions going on there. The multiple choice should be fairly quick, like, hey, look at this one. They want the Ecell, and they kind of set up what should you add? Delta G, how should you go about solving the delta G, and they kind of give it to you. That's going to be your homework. Tomorrow, you will get your test back. Basically what's going to happen with the test is you're going to have an opportunity to take a look at your test and get back some points. But that's going to require you to come in during one of the cub periods to work on it. You can't take it home. Overall, the grades weren't. They were. I expected to get a little bit higher. Some students walked away with high scores. Like I think the high score in this class was like a 93%. Really good. I had some students who got almost all the FRQs correct. And it was just a couple multiple choice that were incorrect. You're a little bit lower than last year, but it's okay. What's going to end up happening is I'm going to allow you to come in. You can actually pick up half points for the ones that you missed. So just kind of come in, you'll work through it. I'll explain the directions to you as far as how you're going to go about approaching it. You will have the opportunity of actually using your notes as well. But you're going to have to write why, you kind of a little bit of your justification for why you went about solving it this way. Because some of them you should have actually seen. Like there was one, I gave you the pH. And I just said, hey, what's the hydronium concentration? And some of you looked at that problem like it was like, oh my gosh, I need to go through ice, I need to go through this, I need to go through that. If I give the pH and I ask for the H3O plus, don't we just simply say, hey, it's 10 to the negative or whatever? That was it. So I don't know if like some ways like, hey, you're getting like, hey, this is way, it must be too complicated. Some of them were pretty straightforward. So tomorrow you'll get your test back. Also, once again, you'll have an opportunity to come in during cub period to kind of look over it. One last thing, so you don't have to run because you got cub period. Does anybody have to really, really run? It's going to be taking like maybe 2 minutes. You got to run.
I have a
You got a test?
Yeah.
Oh, good. Hang on. So basically, what's going to end up happening is this week, I'm going to try to see if we can have one additional meeting of the class during maybe a cub period. And it won't be the whole cub period. It'll probably be like maybe 35, maybe 40 minutes at most. But then what I'm gonna do is I'm gonna give it back to you. Meaning after the exams, normally the rule of thumb is what I take of 1, I give of 2. Meaning that if I get everybody to come in during that time frame, I will end up taking one of your class, like once again, about 40, 45 at the most. But then guess what you get? If I take of 1 and I give of 2, you get 2 free periods out of it. So I'm going to send out an email and try to see which period is going to kind of work for everybody to come in. One last thing, just point out, and then you get out of here. On Friday, you're going to have to use that as a review day. You're going to have it as a review day. You'll come to class, you'll just be reviewing. Unfortunately, it's not something I wanted to do. Never have done this. I won't be here on Friday. And the only reason I won't be here on Friday is my son is getting kicked out of his dorm. So basically the rule of thumb at his school is 24 hours after your last exam, you gotta get out the dorm. Now he's going past the 24 hours. Because once again, I'm in Maryland, he's in Ohio, there's no way I can get to him, get him out of the dorm. But he has to be out. Everybody's gotta be out of their dorms by 2 p.m. on Friday. So on Thursday, I will be leaving school, driving up to him, and then on Friday, packing his room up and getting him out. That's the only reason I will not be here. But that's why I want to kind of build in that additional period to kind of make up for the missing of that Friday. And once again, that additional period is going to probably just be some time where we'll discuss and dialogue about the actual AP exam. Sounds fair? So I'll send an email out and maybe a Google Doc, and you can just let me know which day probably works best for you, and we'll go from there.
Thank you.
All right, you can push that stop.